OK。好，我们继续哦。OK。We have only yeah less than an hour. OK. So this one, OK, as I just said, like n to the power 4 is not so good, right? I mean, it's too high. So we want to see if there's any possible way to get to reduce the complexity. So one possible approach is that we can do repeated squaring. This is like it's actually we are doing like a divide and conquer. Okay, so because we know a to the power of 2k is going to be a to the power of k times a to the power of k, right? So you can compute like a to the power of a squared, a to the power of 4, a to the power of like 2 to the power of log n minus 1. Okay, depending on what your n value is. Okay, so if there are some additional order, of course you have to multiply the rest of the order. But this one, it takes log n squaring to reach the closest like 2 to the power to something to that n value. Okay, so this divide and conquer approach, okay, it's going to help you to reduce complexity from n to the power of 4 to n to the power of 3 log n. It's yeah, it's a divide and conquer, so you can verify this by yourself, okay, and use like a master theorem to easily derive that. Okay, so but this is better than n to the power of 4, of course. Okay, but and also to detect negative weight cycle, you need to check the diagonal for negative values in big O n additional time. Okay, you need to do this again. Okay, and check like because like diagonal basically represent like from I to I, right? From I to I. So if you have a negative cycle, then you just try to run it one more time. Like it must appear, okay, like in the diagonal. So it's kind of just like Bellman fold. So it takes like a linear time. Okay, it takes linear time. So yeah, it looks not that bad. Okay, so this is actually remember like at the beginning of this lecture I said like we are going to introduce 3 different algorithms, right? So this is the first algorithm that we are going to introduce. Okay, we already introduced actually. Okay, and the second algorithm that we are going to introduce is actually like a very famous one. It's called Floyd-Warshall. Okay, Floyd-Warshall. It's also dynamic programming, but it has a twist of mind, and it is a much faster algorithm. Okay, when I say faster, what I meant is like it's n cube. Okay, and well, n cube is better than n cube to log n, right? But it's reduced the log n is not that much. But the idea here, I mean, is very interesting. Okay, that's the most important point. Okay, so again, we define Cijk. Okay, here is the thing. Okay, we try to define this Cijk differently. Okay, so originally Cij m, that m represent the length of the path that we considered, right? But now the Cij, that K actually represents something a little bit special. Okay, first we try to, I know like some number, some vertex may have like A, B, C, D, E, but that's fine. Let's try to rename those vertices from 1 to n, okay? It doesn't change anything, right? We just rename the vertex, you know, with for each vertex we give it a number, a unique number, okay? 就是我们只是给每一个节点一个数字而已嘛。Okay, and then this K means, okay, I don't care how long this path is. I don't care. Okay, but what I care is that you can only use the vertices, okay, in between I to J, the intermediate nodes they use can only be from node 1, node 2, node 3 to node K. Okay. Do you understand what I meant? Okay. So in the intermediate node is allowed only from node 1 to node K. Okay. That is what we meant by the K here. Okay, so let me use this figure. From I to J, okay, you may not have some intermediate nodes. But what we care is that these intermediate nodes, each one, its number must be lower or equal to K. Okay? So, with such a definition, okay, the shortest path from I to J obviously is going to beCijn, right? Because when you put n here, it means you allow the any node to be the intermediate node, right? Because any node will have a number smaller or equal to n, right? So this, if you put this K to be n, then it means that you don't have any constraint for intermediate node. So obviously from I to J, you don't have any constraint for intermediate node. So obviously this must be the shortest path. Okay, but if you constrain it to be under smaller or equal to K, then from I to J, it may not be the shortest path. Okay, and also Cij0, okay, is going to be Aij, okay, the adjacency matrix. Because 0, it means what? It means because you obviously do not have any node. You do not have any node. You do not allow to have any node as an intermediate node, right? Because no node will have its value smaller than 0, smaller or equal to 0. So obviously, like this just means you have no intermediate node whatsoever, right? And if you have no intermediate node whatsoever, that means you can only have direct link from I to J, right? You only can have direct link from I to J. So if you have, so that's like Aij, right? If you don't have a link, if you don't have an edge from I to J, then obviously like it's going to be infinite. Okay. So the interesting point is like this. The Cijk, I mean, here I already told you the initial condition, right? Cij0. How do you get a Cij0? Okay, for every assignment of I and J. And for Cijk, it can be obtained recursively to be mean of Cijk minus 1 or Cik k minus 1 plus Ckj k minus 1. Okay? What does that mean? It means you go from I to j, okay, either you don't use node k at all. Either you don't use node k at all. I mean, for example, you don't use node k at all. You go from I to j. Or if you use node k, okay, then you will go from node I to k, and then from node k to j, right? So either this one is smaller or this one is smaller, right? Right? I mean, theoretically speaking, you could have some loop go out of k and come back, theoretically speaking. But since we do not have, we want a simple path, right? Because we want a simple path. So, we don't want any node to appear in the path twice. So we don't have that. So from I to k and then directly from k to j. Okay, so that's it. So this one, again, can be done just like the previous one. Okay, we can use the matrix multiplication. Okay, the multiplication becomes addition, and the mean is just like basically a loop, and then it's basically a relaxation. So it's like this. So this k represent like this k, and we have I and j. Okay, and we don't need a k there. Okay, because k will be done like implicitly. Cij greater than, if this condition is met, then we replace Cij with this one. Okay, if no a condition is met, basically we just use Cijk minus 1. Okay, so basically that's it. And this is cool because what we want is Cijn, right? Cijn, right? And you can see after we run this, nested 3-level loops, we got Cijn, right? We got Cijn. So this one, okay, it is run in n cubed time, right? And it's very simple to code, and it's very efficient in practice. Very good. This Floyd-Warshall algorithm is a very, very powerful algorithm to compute the all-pair shortest path. Okay? One thing I want to remind you is that, okay, you see that, okay, I never talk about, here in the computation, I compute the weight of the shortest path between node I to node j, right? The weight of the shortest path from node I to node j. But if you say, okay, I want not just the weight, I want the path, what do you do? Okay, this one and the previous one, okay, this is the second algorithm, right? The previous algorithm and this one, basically both tells you like the weight of the path, right? But it doesn't tell you the whole path, right? What I want to tell you is that, okay, when you change this, what does that mean? It means that the intermediate node contains node k, right? The intermediate node contains node k. Okay, if this condition is met. So what you need to do is to remember which case is going to change. I mean, when this condition is satisfied, then you need to insert this node K as the intermediate node between node I and node J. Okay, I will leave this one for you to think. Okay, but I just want to point out, when this condition is met, that means K should be included as an intermediate node. Okay, just like here. Okay, you should go through here. I mean, not directly go from I to J. You should go through here. That means what? K is part of the shortest path, right? Okay, so this is something you need to remember. Same thing goes for the previous approach. Okay, and also Floyd-Warshall. Okay, you can use it to compute the transitive closure of a direct graph. What does it mean? Okay, transitive closure just represent like if there exists a path from I to J, we will make it 1. Otherwise, it's 0. So you can use exactly Floyd-Warshall, but use like or and and. Okay, use you don't need to compute the value. You just need to remember like is there a way to go through to go from I to J. So use a Boolean operation. It's good enough. Okay, don't use a min and a plus. Use or and and. That's good enough. For example, this Tijk is going to be Tijk minus 1 or Tik k minus 1 and Tkj k minus 1. This means like be careful. Okay, so I mean if you can reach, I mean go from I to J by using the intermediate nodes. Okay, from node 1 to node K. Okay, it means if this is I mean whether or not this is true, it depends on. If you don't need to use node K, you can already go from I to J. Obviously, this is true, right? Or, I mean, you need to go through K, or you need to go through K. I mean, from I to K without using K, okay? And if this is true, and then you can go from K to J without using K, okay? I mean, if both are true, you can go from I to J by using the node 1, node 2, up to node K, okay? Or you don't need to use a node K at all. Okay, something like this. And the complexity is exactly the same, n cubed. Okay, and also I also want to remind you, okay, the Floyd-Warshall algorithm, okay, can also be used to construct a distributed Floyd-Warshall algorithm. Okay, in other words, I mean, these nodes that we are talking about, they could be different entity on the network. Okay, in the network, we can use Floyd-Warshall algorithm to compute the shortest path between different nodes. Okay, the algorithm could be run distributively, and then we can still get the shortest path. It is cool, but of course it's going to require higher complexity because like we are going to talk about message passing. So message passing from one node to another, sometimes it takes a long time. Okay, because network, I mean, because we are talking about network, right? I mean, of course, like the internet you are talking about nowadays, like if you sit in front of your computer, you can access the internet so quickly. But in distributed computing, I mean, the delay between two nodes is considered like I mean, very large. It could take a long time. Okay, so but anyway, just want you to know. Okay, you can even use distributed. There's even a distributed version of Floyd-Warshall. Okay, I used to teach like a distributed algorithm in our department, but yeah, I haven't offered this class for quite a long time, probably 4 to 5 years. Yeah, but anyway, that's the Floyd-Warshall algorithm. Okay, so that's the second approach for all pair shortest path. Okay. And then, okay, let me remind you, the best algorithm to find the all-pair shortest path is, so far, is n cubed, right? N cubed, where n represents the number of vertices, right? Okay, so look at here. If you're able to use Dijkstra algorithm, you see this one is still better than n cubed, right? This VE, you say, oh, VE is pretty much n cubed. Well, I cannot say you are wrong, but it depends on what your graph is. If your graph is dense graph, this part is n cubed. Yes, that's true. But if your graph is not so dense, or put it another way, if your graph is sparse, then this V times E could be much lower. Okay, it's going to be between n squared to n cubed. Okay, and this one is, well, n squared log n pretty much. I mean, you know, if your graph is not dense, then this is considered cheaper than n cubed, right? Cheaper than n cubed. So if we are able to use the Dijkstra to solve the general case, wouldn't that be nice? Right? It would be nice if we can use Dijkstra, run Dijkstra like n times. Then that's a simple approach, and we are able to solve. We can even use a smaller time complexity for that. So it is quite good, but the issue is general case. I mean, Dijkstra doesn't work for like a negative weight edge, right? So how do we do? How do we do? Okay. The idea is that we could use graph reweighting to convert the weight, okay, the negative weight edges into positive weight. Okay. So we are given a function h, okay. We call that function reweight function. So each edge, okay, you know, if you do the reweight, okay, this reweight function, okay, first I want to make it clear. This reweight function doesn't directly apply to edge. It applies to node. It applies to node. Okay, so you know h applied to node, so you can see it's V2R. So it apply to a node and you get a value. But once you use the reweight, okay, each edge from U to V, okay, it's going to be the original weight, okay, plus the weight of U minus weight of V. Okay, so this reweight, okay, you apply this function to your node to get a number, and then you indirectly change the weight of your edge, okay, from the original value to, okay, to the plus HU minus HV. Okay? So for any two vertices, all paths between them are reweighted by the same amount. Okay? So if we have a path from V1 to Vk, this is one path. Okay? Then you see after the reweight, okay, WHP is going to be WH VI to VI plus 1, okay, from I to k minus 1, right? We know that. So we plug in this thing for every edge. Because obviously, okay, we have this term, okay, for each edge. So you see like the later one is going to cancel out the previous one of this one. So, I mean, if you try to list everything here, you see that only thing that's going to left is going to be, this part is going to, remain. This part is remain, going to be there. So you have WP, but you are going to have HV1 minus HVK, right? All the intermediate, like the HV2, HV3, HV4, blah, 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 they all cancel out each other, right? So what do we mean by here? It means like no matter which path we are talking about, if you have multiple paths from V1 to VK, if you have multiple paths, regardless of the length of your path, okay, 就是你的长度不重要啦，只要你是起始点是 V1， 终点是 VK，OK， 那他们都会加一个 HV1， 减掉一个 HVK， 就加上一个 reweight 的这个起始点的 reweight， 减掉一个终点的 reweight， 所以 in other words, this part is the same amount for any path. Is that right? 对不对？对不对？我刚刚给你看说，这是一个 one path, but this can be applied for any path between V1 to VK, right? So, okay, obviously, this is also true for shortest path, right? This is also true for shortest path. So the reweight, after reweight, the shortest path from U to V is going to be original shortest path weight plus HU minus HV, right? We have this directly from the previous discussion, right? Okay. So think about this. Okay. We could do something like this. Okay. We could find a function h, okay, such that, okay, we try to make WHUV greater or equal to 0 for all UV. Try to change every path to be greater or equal to 0. Okay. Once we finish that, because this graph contains no negative edge, right? No negative weight edge. So we can apply Dijkstra algorithm from each vertex on this reweighted graph, right? To obtain this one, right? To obtain this one. But once you obtain this one, you can get this one by minus HU plus HV, right? It's a simple math, right? You see what I'm doing? 就说你原来的那个 Dijkstra 不能用，对不对？我们用 reweight 不是直接用在那个 edge 上，但是它可以 indirectly 把那些那个 edge 的那个 weight 改变，对不对？那我们想办法找到一个这样的方选，让这个 edge weight 都变大于等于0的。那这样子的话，我们就直接去算这个改变以后的 graph 的那个 shortest path， 用 Dijkstra 去算 ，Dijkstra 算每一个那个 pair 都去把它的 shortest path 算出来以后，你这个算出来以后，那你又知道这个又知道这个，那你这个是不是就知道了？对不对？对，其实就是你间接的去算 HUV 啦，对。但是那你要怎么知道这个 reweight function？ How do you get that reweight function? So your point is to, you want the you have like you have H that apply to every vertex, right? You want to apply H on every vertex. V1, you want to apply HV2, HVK, Vn, right? Right? You want to find right assignment for this vertex to accomplish your goal, right? Okay. Okay. What is your goal? Your goal is because your new WHUV, your WHUV is going to be WUV, which you know already, right? This one you know already, right? Plus HU minus HV, right? 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 And you want this thing to be greater or equal to 0, right? Right? So you want this one to be greater, this thing to be greater or equal to 0, right? 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 In other words, you want this thing to be greater or equal to 0, right? 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 So in other words, what you want is you want WUV to be greater, greater or equal to HV minus HU, right? This is what you are looking for, right? Right? For every age, you have something like that, right? So far, so good, right? And you know this value. This value you know. You know this value. Okay. Let me write it to make it more obvious for you. Okay. Can I put this one to be x1? Make this one to be x2. Make this one to be xn. Can I do that? I could, right? I could do that, right? Then this one will be the spatial linear programming question we just dealt with. Remember, at the end of the previous lecture, we used Bellman-4 to solve the special case of linear programming with like two variable, like one variable to have coefficient 1, one variable have coefficient -1. So this is one variable, this is another variable, coefficient is 1, coefficient is -1. Right? So sorry. So we end up, sorry. Shit. Okay, we end up to have, okay, we end up have this one. And we can, as long as we can guarantee we have every age, we can have HU and HV value smaller or equal to WUV, and this way will help us to use the Dijkstra algorithm to solve like the shortest path. Okay, because like every age is going to be positive. Okay, I mean, well, greater or equal to 0. Okay, so the idea is like this. We find a function. Okay, this function actually is an assignment. This assignment is exactly how you, I mean, what we did to solve that linear programming. Okay, you know, such that like to make like a WHUV greater or equal to 0 for all UV equal to E, by using, after we have that, okay, I mean, how do we do that? We can use Bellman-Ford to solve the difference constraint. HV minus HU smaller equal to WUV. WUV is known. This HV and HU are xj and xi that I mean from here. Okay, so we have like a bunch of this inequality constraint, and we use Bellman-Ford to solve it. And how much time does it take to solve this? Of course, this has to have no negative wave cycle. If there's negative wave cycle, we cannot solve it, right? Is it possible to have negative wave cycle here? It's possible. You may not have any possible reweight function that that do this, but if you don't have that, I mean, most likely you don't have shortest. I mean, the original graph has no solution at all. Okay, so basically, okay, how much time does it take to solve this? We already know it's big O V times E, right? Okay, and then after you change this, it takes, you just run a Dijkstra algorithm on this new graph, well, which is the same as the previous graph, but the weight of each edge will be different, right? Will be changed. And we guarantee each edge, the weight is greater or equal to 0. Now, so we run the Dijkstra algorithm from every node, so it takes this much time, right? And once you get like a delta HUV, the delta UV will be delta HUV minus HU plus HV. And because we have this V squared, this many pairs, right? So we need to do this computation for every pair. So it's like a big O V squared. So how much time exactly are we talking about? It's going to be this one plus this one plus this one. Okay, this one is upper bounded. This one is absorb this one, right? Okay, this one absorb this one, and this one, obviously, this one absorb this one too, right? So you can see the complexity is total time is going to be big O VE plus V squared log B. Okay? Is it okay? Is it good? So this is the third way to compute all pair shortest path, which is by now the cheapest approach. If your graph is not dense graph. If it's dense, it's pretty much equivalent to n cube. Okay? That's it for this class. Okay? Any question? So we finished like the shortest path discussion as I promised. So next week we are going to talk about NP complete. Okay? I don't think I can finish NP complete and the min-max flow in one lecture. So I'm going to drop min-max flow. Okay? Compared to min-max flow, I think NP complete is perhaps more important. Okay? So yeah, that's it. I think you have all the handout, I mean, including min-max flow, but we are not going to talk about min-max flow. So if you are interested, you can read it by yourself. I'm sorry, I just don't have enough time. Okay, but as I said, I already covered much more material than last time I covered this class, so I'm satisfied. Okay, so and I don't want to rush. okay, to cover more material. I think like the pace is should be okay. It's not too fast, it's not too slow anyway. Okay, so any question? If no question, I will see you guys like next week. Okay, next week will be a final lecture, and then we will have final exam. Okay, final programming exam and the final exam in the next week. Okay, I already told you. Okay, the sign up sheet for if you want to use your laptop for the programming exam. The sign up sheet will be available from 12 o'clock today. Okay, so another 10 minutes. Okay, so the first 20 students sign up on the sign up sheet will be able to use their own computer to do the programming exam. But you are required to record your screen, okay, so that we know like you are not cheating. Okay, I'm sorry, but at least you get to use your computer, which is should be much more convenient for you. Okay, so any question? Okay, see you guys next week then. Bye.